Let's get into Bernoulli's equation. The equation says work done per unit volume of a fluid by the surrounding fluid is equal to sum of changes in kinetic and potential energies per unit volume that occur during flow. Now assume that this is a tube through which flows fluid. The area of cross section is very narrow over here, whereas it's quite broad over here. Now these are two sections RS. This is one section or one column which we are to consider, and this is yet another column which we have got to consider. Now as per Bernoulli's equation, what we have got to prove is when water flows in from here and when water flows in from here, same water is coming from here and flowing this way. So when water is flowing here and when water is flowing here, now this column is at a height h1 from base and this column is at height h2 from base. The difference between the work done by flow of fluid via column PQ and via column RS is equal to difference in potential and kinetic energy of these two columns. That's what is Bernoulli's equation. That's what we have got to prove. So for that, what we have got to do is we have got to set a formula for work for fluid flowing here and work for fluid flowing here. Then we also have got to find out potential energy, kinetic energy over here and potential kinetic energy over here. So let's get into the process. So we know basic formula for work is force into displacement. Now we have got to talk about force in this section. All right. Now we know pressure is equal to force upon area. So force would be, we multiply pressure with area. So force would be P1 A1. So F1 force over here is P1 A1, where A1 is area of cross section and P1 obviously is pressure over here. Similarly here also it would be P2 A2, where A2 is area of cross section for this section. Alright, so force is done. And S is the distance. S is the distance. So here it is D1. So fluid traveled distance D1, fluid traveled distance D2. So we got force F2 we got, which is P2 A2, whereas F1 is P1 A1. So formula for F is ready with us. So we can also find out formula for work, which is for this it would be W1, which would be equal to P1 A1 into D1, whereas for this it would be P2 A2 D2. Now we have got minus here. Why? Because as I have indicated by arrow, in this case what is happening is the direction is this side, whereas here it's opposing this force, right? Since displacement of fluid is being opposed by this section, so we have negative over here. Alright, so our aim was what? Our aim was to deduce net work. Alright, difference in work, that is net work. So net work done would be W is equal to P1 A1 D1 minus P2 A2 D2. A1 D1 A2 D2 is what? Is volume. Now come over here for that. dV A2 D2, that is area into this distance, gives us what? Gives us volume. So dV is equal to A2 D2. Same way here also A1 D1 is equal to dV. Now this fluid is being passed via this column PQ in time dt, and here also in time dt. Now we would find that same volume would flow through this column as well as via this column. So that's the reason why A2 D2 is dV and A1 D1 is also dV. So we put in, so instead of A1 D1, A2 D2, we put in dV, and then we take dV common. So our formula for net work done is P1 minus P2 into dV, where dV is flow of volume at particular time dt. That's most important. So at that particular time, 2 seconds, if it is 5 ml flowing in, here also in 2 seconds it would be 5 ml flowing in. So that's what we mean by same dV. Alright. So net work done. Now let's get into derivation of potential energy and kinetic energy. Potential energy, kinetic energy, potential energy, kinetic energy over here, potential energy and kinetic energy over here. Now just for information, this is also called as work energy theorem, obviously, because we already found out work. Now we are finding in terms of energy. So it's also known as work energy theorem. All right. Now to begin with, the volume pass through this in dt time is dV. That's what we already saw. And same way volume passed over here also is dV, which we already saw. Now kinetic energy we know is half mv square. Then how do we get half rho a2 d2 v2 square? Just for your information, this v2 and v1, whatever you see, v1 v2, whatever you see, it's velocity, is the speed. V is the speed. All right, here just let me clarify. Now when we come to finding out energies, this we have already found out. dV, a2 d2 and a1 d1 both are dV. Volume passed through this at a particular time dt is dV. We have already seen that. Now another V comes here. Now this is V2 and this is V1. Now whenever we mention V1, V2, it's concerned with speed of flow of fluid through relevant columns. Alright. So now let us get into finding kinetic energy. We know kinetic energy formula is half mv square. But then how is it half rho, which is density, a2 d2, we know is volume, and v2 square, that is velocity. Yes, velocity. So there has to be this relationship. This relationship we have already done. Rho into v is mass. How? Rho, that is density, is equal to mass over volume. So mass is equal to rho into v. Alright. Now rho into v. So this becomes, this rho into v becomes mass, and v2 square is the velocity. So the formula for kinetic energy becomes half rho a2 d2, that is this, that is dV for this, into v2 square. So this becomes the formula for kinetic energy. And for potential energy, it is rho dV gh2. Now how do we get this? Now when we check out over here, potential energy formula, basic formula is mgh. Gh is available here. Again, rho into dV. That is density into volume, dV. So that becomes your potential energy. So this becomes mgh. So this becomes the potential energy for this section, and this becomes the potential energy for this section, since it is at height h1. So h1, and since this column is at a height of h2, so you have h2 over here. So that's the formula. Pe is equal to this, k is equal to this. So kinetic energy is this, potential energy is this. So we got formula for both kinetic energy and potential energy in both the sections. Now what do we have to do? We just have to subtract kinetic energies and potential energies. So this is what we do here. So we subtract kinetic energies over here. All right. This is kinetic energy over here, subtracted by kinetic energy over here. So when we do that, we know a2 d2 already proved, which is equal to dV, because it's the same volume of fluid passing through both the columns at a particular time dt, at a specific time dt. So this becomes dv. So half rho dv v2 square minus half rho dv v1 square. Alright, so when we do it, we can take half rho dv as common. So it becomes v2 square minus v1 square. This becomes the formula for change in kinetic energy from here to here. Similarly, we can also get into change in potential energy here and here. We just do that, and what we end up with is rho dv g h2 minus h1. So net change in gravitational potential energy during time dt. These are two changes in kinetic energies and potential energies that we have derived. So our next mission is to correlate this mechanical change with work. Alright. So what do we find here? Total change in mechanical energy is equal to change in kinetic energy plus change in potential energy. So we just set in those formulae. Just for clarification, I have written this in red and this in blue. So this is change in kinetic energy plus change in potential energy. Also, net work done by fluid on passing from PQ to RS section is equal to, so this was work done, is equal to change in mechanical energy, change in mechanical energy. So we put in this formula already we had derived for work, and this is which we derived right now, change in mechanical energy. Then, so this is our formula. Now if we intend to find work done per unit volume flow of fluid, then we convert this to 1. We substitute this as 1. So we get this formula. Alright. So this becomes our formula for work done per unit volume flow of fluid. So the equation can also be written as pressure 1 plus half rho v1 square plus rho gh1 is equal to P2 pressure 2 plus half rho v2 square plus rho gh. Alright. Or we can also say that it is constant. Now just to keep in mind that this v is velocity. Alright. So that's all about Bernoulli's equation. Alright.